Okay, this exercise 13.3, just doing a part 5 here, domains and equations, looking at domains and equations of tangents for logarithmic and exponential functions. So just an example from question 2, state the largest possible domain of this function and find its derivative. So if we look at any log function, you can only substitute in values here of x greater than 0. So if you put, for example, ln 0 on your calculator, it's error or undefined. ln of, say, a negative, again, undefined or error. So you can only take the ln of a positive number. So here, in place of x is the x plus square root of x. That has to be positive. But we do have restrictions on the square root of x. We know that you cannot take the square root of a negative, so x must be greater than 0. Well, it can be greater than or equal to 0, but because you can't take the ln of 0, then x must be greater than 0. So the domain for this function here is that x is greater than 0. And now just looking at the derivative, if y equals log to the base 2 of x plus root x, then the derivative, remember, the rule is if y equals ln of a function of x, then the derivative dy dx is f dash x on fx. So you differentiate that and you get 1 plus. Now remember, root x is x to the power of a half. So if you differentiate that, you bring the half to the front, write the x out, drop the power by 1, over x plus over the original function. So this is the derivative over the original function. Now we can write this as 1 plus 1 over 2, and this x to the negative half can go down here as x to the positive half, or root x there, all over x plus root x. Now what we want to do is we need to make this look a little bit better. So I'm going to write this all with a common denominator. So actually, I'll write it separately first. I've got 1 plus 1 over 2 root x. All of that numerator is divided by x plus root x. So I've got this divided by x plus root x. So I've written it as, I've broken the fraction up, okay, because we don't want fractions within fractions. So I'm going to make a common denominator here, and I've got 2 root x plus 1 all over 2 root x. Now, instead of dividing by that, I'll times by 1 over that. Okay, so now I can simplify that. And on my numerator, I've just got 2 root x plus 1 over, and then I have to multiply this by that. So I would have 2 root x times x, which is 2x root x, plus 2 root x times root x is 2x. Okay? So, yes, we can just leave it like that. Or if you want, you could factorize out, might be able to do some factorizing. Looks like I've got 2x as a common factor, and then I've got root x plus 1. But again, there's no simplification from the numerator, so there's really no need. So 2x, common factor, root x plus 1. So there'll be no cancellations there. Okay? Just maybe another example from that, I'll look at 2c. So looking at the function of x is log to the base e of x squared minus 4x plus 4. Again, we know that you can only take the log. If I even put function of x here, it's fine. You can only take this function of x must be greater than 0, because you cannot take the log of a negative or of 0. So we know that x squared minus 4x plus 4 has to be greater than 0. This is a concave up parabola, so I could factorize it. It's actually a perfect square. So x minus 2 squared has to be greater than 0. So obviously this is a parabola. It's concave up, and it's shifted 2 units to the, this is what it looks like. Okay? This is what it looks like. This is actually the sketch of that parabola, x minus 2 squared. If I was to sketch y equals x minus 2 squared, we know that that is the parabola x squared shifted 2 units to the right. So where is this parabola greater than 0? Well, it looks like this parabola is greater than 0 for all real x. So remember, it's greater than 0 there, it equals 0 on the line, and it's less than 0 below the line. So it's actually, the domain is not just all real x, it is all real x except for x cannot equal 2. Because if x was equal to 2, then this would equal 0. So the parabola is shifted 2 units across to the left, but you have to be above the line, not on the line, not on the x-axis. So the domain is all real x not equal to 2. Now the reason is, if you look at this, when x equals 2, you get 4 minus 8 plus 4, which is 0, and you can't take log, you can't do ln 0, it's undefined. Okay, and then just the derivative of the log will be the derivative of this over the function. So it'll be 2x minus 4 over x squared minus 4x plus 4. So that is the derivative of this. Okay. What you want to do is just see if you can simplify it. 2x minus 4 can be factorized, so that's 2 bracket x minus 2. But if you actually look at x squared minus 4x plus 4, you can see that it's actually a perfect square, that it's x minus 2 all squared. So we actually can simplify this, because one of the x minus 2's here cancel with that, so you get 2 over x minus 2. Okay? So just be very careful with that sort of question. Sketch the graph of y equals log to the base e of x minus 1, stating the largest possible domain. So we know that normal log to the base e of x looks like this. That's the ln x curve. Now this has been shifted 1 unit to the right. So if you want to sketch that, that normally cuts through at 1, because ln 1 is 0. So when you now substitute, when x is 2, you get 2 minus 1 is 1. So it's shifted 1 to the right. This will now be ln 2. Before we had the asymptote here, the y-axis was an asymptote. Now everything is shifted over 1 unit to the right. So the line x is 1 is now the asymptote, and it will cut through 2 here. So this is the curve of y equals log to the base e of x minus 1, because it's log to the base e of x shifted 1 unit over to the right. Okay, now therefore you can see here that the domain is that x will be greater than 1. However, what we could have done is we could have looked at the original function. Okay, so if I go back and look at the original function of y equals log to the base e of x minus 1, the other way we could have worked out the domain is that I know that this x minus 1 has to be greater than 0, so therefore x has to be greater than 1, and that's my domain. Now to, so we've looked at that, and now the equation of the tangent to the curve. We've done all this in prelim, so you're now just doing it with log functions. So you've got that y equals log to the base e of x minus 1. Remember, if you're wanting equation of tangent to the curve, you need the derivative, and that will be f dashed x on fx. And the derivative of x minus 1 is just 1 over the original function. The function of x is x minus 1 there. And when x is 2, you can find the gradient to the curve. So the gradient will be 1 over 2 minus 1, which is 1 over 1, which is 1. So the gradient of the tangent when x is 2 is 1. But also when x equals 2, you need to find the y value of the equation. So y is log to the base e of 2 minus 1, which is log to the base e of 1, which is ln 1, which is 0. So our point is 2, 0, and our gradient is 1. Okay, so this one's not too complicated at all. If you want just now finding the equation of the tangent, you would use your point gradient formula. Y minus y1 equals mx minus x1. Now you've done this all before in prelim. So it'll be y minus 0 is 1 bracket x minus 2. And you just end up with that y equals x minus 2. And we'll just look at one more question. And the equation of the tangent to the curve y equals 10 to the power of x at the point 1, 10. Okay. Now remembering equation of tangent, first you have to differentiate. So dy dx is, now remember, if y equals a to the function of x, then this is on your formula sheet, dy dx is ln a f dashed x a to the function of x. That's what's on your formula sheet. So you can differentiate 10 to the power of x and you will get ln 10. The derivative of this function, derivative of x is 1 times a to the function of x is just what's there, times 10 to the x. So this is ln 10 times 10 to the power of x. That's your derivative. Now we want the equation of the tangent at the point 1, 0. So when x is 1, the gradient, dy dx, is ln 10 times 10 to the power of 1, which is 10 ln 10. And now we want the equation of the tangent, and you would just use your point gradient formula. So y minus y1 is mx minus x1, and your gradient is 10 ln 10, and your point is 110. So you just get y minus 10 is 10 ln 10, x minus 1, just expanding, y minus 10 is 10 ln 10 x, be careful, because that's the coefficient of the x, minus 10 ln 10. Okay, and now we can just take this 10 over. We get y equals 10 ln 10 x minus 10 ln 10 plus 10. And so here I've got my y term, my x term, and here is my constant term. If I wanted, I could take out 10 as a common factor. So I'm going to go plus 10. I'm going to do this one first, 1 minus ln 10. Or I'd have to put a negative there if you wanted to write that one first. But I think it's better to do the plus 10 times 1 and then the negative in here. Okay?